Hi, I'm Igor, CEO and founder of Solvi, and with me today is Cody Thomas from Advexture. We are in Northern California, where we will take the all-new Mavic 3 Multispectral for a test drive in the real-world conditions. Cody, can you tell us a bit about the field and what we are about to do here?
Yeah, absolutely. This is a 60-acre tomato field, and these plants were just transplanted about 3 weeks ago, so they're quite small. Today, we're going to fly the field, we're going to process that data in Solvi, and we're going to get some plant counting information from this field. With the plants being this small, it's going to be pretty tough to spot variability, but as they mature, that's going to become a lot easier to quantify. I'll come back out one more time and fly at the end of the season, and we'll see some added variability throughout the field, see how this field does overall throughout the course of a growing season. So it'll be some interesting information for the grower to take a look at.
Right. And this will be a very hands-on demo, so we'll look into the hardware on the new Mavic 3 Multispectral. We will walk through how the flight planning works and things to consider when you're planning the flight. We will look at the data in the field to make sure that all the captures are in place and the data is good before you upload it to Solvi. And then, of course, we will dive deep into the analytics and show how to generate the counts for this field, how to spot all these potential issues. And by the end of this demo, we'll provide the grower with very detailed information that will tell them how successful the establishment of this tomato crop was.
Yeah, exactly. There's going to be a few challenges when the plants are this small, so we have to adjust flight altitude to compensate for the size of the plants. What's our GSD?
So we should be aiming at about 1 centimeter. So the plants are small, but they're not too small. About 1 centimeter pixel should be good.
So we're going to fly at about 100 feet over 60 acres. There's a lot of plants out here. So this is going to be very interesting to take a look at after we process it to get a head count. But another challenge is there's weeds out there. So we're going to see just how well Solvi does with mapping the plants going through weed patches. So that's going to be a nice little challenge to take a close look at.
Absolutely, absolutely.
So the Mavic 3 Multispectral is a nice, compact, easy to transport unit. Tucks away quite nicely here in this case. And you just unfold the arms here. Comes with an RC, remote controller. Also comes with an RTK module. So if you're going to do any R&D projects, if you're going to map fields for the purpose of spot spraying with a drone or even manned aircraft or a ground rig, this is going to come in quite handy. The M3M is a 4-band multispectral unit here. It's missing the blue band, but it has the green, red, near infrared, and red edge bands, along with a 20 megapixel RGB camera. On the back of the unit, we have a light calibration sensor. So being able to get the radiance information during that point in time in which you're mapping is incredibly important when measuring variability in the field, so you get proper reflectance information from the plants from these bands. It's very important. Today's flight, we're going to walk you through how we're going to map this field with these small plants. And as you can see with the plants, they're quite small, as we mentioned before. So we're going to fly at 100 feet. That's going to be about 1 centimeter GSD. And we're going to run that data through Solvi. So we're going to create our flight plan now. And the first thing you want to do is set your flight boundaries around the field. So in this case, this field is kind of the shape of a rectangle. And I'm going to draw the boundaries around there. It's typical to fly at a 75% overlap. In this case, since we're going to fly quite low at 100 feet, I'm going to do a 65% side lap and 75% front lap. And we're going to fly at about 8 miles an hour. That's just the standard recommended flight speed here within the app. I like to toggle the dewarping selection as well. And we're going to upload the mission, and we're going to go ahead and we're going to take off. Okay, so since this field's pretty big, we have to do a handful of battery swaps. Pretty normal on large fields. So put a fresh battery in, turn the drone back on, and the drone's going to pick up where it left off. Okay, we're done with our flight. What we're going to do now is we're going to pull the SD card, and we're going to do a little bit of QC, make sure that we collected all of the imagery over the field, and we're going to run the data through Solvi. So what we're going to do is we're going to install the SD card into the laptop, and we're going to do a quick QC on the data. What we want to do is double check the image footprints over the field, make sure images are taken, make sure there's no gaps in the field between images, and then we're going to start our upload process.
All right, now that we are done collecting the data, next step is to upload imagery to Solvi so that it gets stitched into the maps. And then once we have the maps, we can continue and create the plant counts. But first, let's have a look at the images that we've collected. So I moved over all the imagery from the SD card to my computer. That's something that I would recommend to do before uploading the images. And I moved them into two separate folders, one with multispectral imagery and one with RGB. We can see that multispectral imagery has 4 images for every capture. So we've got green band, infrared band, red band, and reddish band. And then for the RGB imagery, we have 1 image per capture. So all 3 bands are in a single JPEG file. We can also inspect closer the images and just take some random samples and see what it looks like. And we can see that the plants are very clearly visible. That's very important for accurate plant counts. There are no blurriness in the imagery, that it's crisp and sharp. So that looks good. The next step is to upload the imagery into Solvi. And to do that, we will head over to Solvi's website. And then once logged in, we'll click Upload Images here, select the Overlapping Images option, and then just select all the images in the RGB folder, either by clicking Ctrl-A or by selecting the first image, holding the Shift button click, and then the last one. So we can see here that we've got 2,792 images, so quite a big data set. So we'll just select all those images and click Open, and in the next step, Solvi will show the preview of where the images were taken. And this is really a good quality control step to make sure that you are selecting the right imagery, that all the images were captured correctly across the whole field, and you've got the whole field coverage. So we get this nice preview here where the white dots show the image captures. We can see here that for the most part of the field, the images were collected correctly and nicely. But towards the end of the field, there are some gaps. As it turned out, it was just an issue with the GPS. So the images were actually collected with the same equal distance interval as in the rest of the field, but just the GPS location was recorded incorrectly. So that's not a big issue, but that's a typical kind of thing that you want to watch out for and make sure that you don't have issues like this while you're still in the field, so you can recollect the data when needed. So to upload the images, we just need to select the right farm and field. That's something how data is organized in Solvi, so it can easily be shared with others. So we'll select the tomato farm here. We'll click here on the field and select tomato field. And then for the crop, we'll specify tomato. And then we'll just click upload. And now the imagery is being uploaded. As they get uploaded, we can see that the dots turn into the green. And once the whole data set is uploaded, the processing will start automatically and can take probably 2 or 3 hours because this is a fairly large data set, but we'll receive an email notification, and after that we'll be able to dive deep into the analytics. Next, we will repeat the process with multispectral images and just select all the images again. We can see here that we've got almost 11,000 images here, and that's because multispectral camera takes 4 images per capture. But the only difference here is that for the multispectral imagery, we will also want to include the shots of the calibration panel. We can either opt in to just use the DLS, so the sunshine sensor, but for the most reliable calibration results, it's recommended to also use a reflectance panel. So I'll just click here on Add More Images, and in the calibration folder here, I've got the images of the reflectance panels that we've taken. So I will just select all these images and upload them together with all the other images. And during the processing, Solvi will automatically recognize these calibration images and use them for calibration in addition to using the data from the sunshine sensor. So I'll just hit upload here and now upload all these images as well. Next, we'll detect the plants in the whole field, and to do that, I've switched over to the RGB version of this data set, and I will toggle the PlantAI tool here and create a new detection. There are 2 options here that we can see. You can either request detection from Solvi, then our support team will process it for you, or you can generate the counts yourself, and that's what we will do for now. So once the PlantAI tool is open here, we have this example area. And here is the important concept to understand how the tool works. So instead of working with one type of plants or specific types of plants, the tool actually learns about the plants that you want to identify in the imagery by the examples that you provide to it. So here we have one example area where we need to circle in a set number of plants. So usually 10 to 20 plants is a good starting point. And what will happen then behind the scenes is that from this example area, the training data will be generated and that training data will be used to fine-tune that AI model that we have developed at Solvi to detect a lot of different types of crops. So I will make this rectangle a bit smaller so that it covers approximately 10-15 plants, and then select the circle tool here and draw the circles so they are big enough to outline all the plants. One thing that is also important to understand here is that everything within this example area that is not circled in is also used for training as something that shouldn't be detected. So that's a great way actually to make sure that the weeds are not identified as plants, or you can actually work in the opposite way. Say you want to identify the weeds and not the plants. So you would just do then the reverse version. You would circle in the weeds and leave out the plants. And then the AI tool learn that way that it should focus on weeds instead of plants. So now that we circled in a few plants here, we can click to continue. And in the next step, we will get this test area here. And the idea here is that you can try in a smaller area of the field how well it will work in your specific case. Because you can literally use this tool on all types of crops, anything from corn, soybean to trees to different specialty crops and so on. So in this step, we just want to try and see will it even work in my case. So I will click Run Test Detection, and what will happen now behind the scenes is that Solvi's PlantAI model will be fine-tuned with this specific data that we have provided here. Then the detection within this smaller test area will be run, and we will get to see the results. After that, we can choose either to cancel the workflow and exit the tool, or if we are happy with the results and think that it will work in the whole field, we can continue to the next step. So let's see what kind of results we get in a few minutes. Now we have the results of the test detection in here, and we can review the results. But we already kind of can see that the tool did a really nice job of identifying all the plants in the rows here. If we zoom in here, we can see the red circles here outlining the plants. That's what the tool identified. But we can also see that it identified some weeds here as plants. But as I mentioned previously, this can be quite easily improved by providing another set of examples and outlining just the plants and leaving out the weeds. And that way telling the tool to ignore these types of weeds. So overall, the results look really promising. So we just click to continue with the whole field. And we've got a few more options to choose here from before running the detection in the whole field. So first we choose if we want to do the basic detection. That's useful for crop like corn or soybean, where we just want to count all the plants. Or we can choose detection with plant level data, where that's interesting for specialty crops, trees, and so on, where you want, apart from just counting the plants, also measure the size of each plant and calculate the health. So we'll go with this second option. And in the next section, we can actually choose what kind of plant level data we want to generate for each plant. So diameter and area of the canopy is pre-selected here. And for the health, we can choose from a variety of different vegetation indices. So let's choose GLI and Vary. We also have row and gap analysis option that calculates the distance between all the plants and helps identify abnormal gaps, and a few other options down here, which we will leave unchecked for now. And finally, we get the price summary. So depending on the type of detection that we want to do and the area of the whole field that we have adjusted here, the price will be calculated and presented here in the summary. So finally, now that we've done all these selections, we can kick off the plant detection, and now the detection will be run in the whole field. It's going to take a little bit longer, maybe 10 to 20 minutes, depending on exact size of the field and resolution of the imagery. Okay, now we've got the results for the whole field, and we can more closely inspect how the tool performs in different parts of it. In this step, I like to switch off the background map so that it's easier to spot different patterns that are not normal. For example, in this area, we can see that big gap here, and it could be that plants are actually missing there, but it could also be that the tool misses them for some reason. So we can zoom in closer, toggle back the background map, and indeed it looks like there are some plants here, but they are very small. So probably that's why the tool missed them, but that's really easy to fix. We just need to add more examples there, and in the next iteration, the tool will hopefully recognize them. To do that, we'll click Provide More Examples button, Add Examples, and then adjust this blue array here so that it covers this whole part where the plants are missing. Choose again the circle tool, and similar to how we've done previously, we circle in all these small plants. Again, super important to make sure that all the plants are circled in. We are not missing any of them. After that, we can zoom out and see if there are any other issues that we can fix. And in this field, it's obvious that there are some spots with weeds. So if we zoom out a bit, we can see that there are some parts of the field where between the plants and between the rows, there are some weed nests. So to improve this kind of issue, we again add more examples. And now we will include patches with the weeds in this blue box, but we'll only circle in the plants. So that's how the tool actually learns to ignore the weeds and only focus on the plants. So we'll keep drawing the circles here where the plants should be, just like that. Okay, now we've created 2 more sets of examples, and we can run the next iteration and see how the results will improve. So we just click continue. In this step, we don't need to change anything because we've already chosen all the output options that we want. So we just click detect plants, and we'll look how it turns out in the next step. So the second iteration is now ready, and we can see that similar to the first iteration, we've got roughly the same number of plants in the whole field, so a bit more than 500,000. But in this case, there are 10,000 plants more compared to the previous iteration. And that's a sign that all those gaps where the tool was missing the plants should now be fixed. And indeed, if we look at the map in the previous place here, there were some gaps, and now it's gone. We can zoom in a bit more, and we can see also all those blue polygons, which are the results of the previous detections where we had a lot of weeds detected as plants. It looks like now those detections are gone as well. If we switch off the previous results of detection and only leave the latest one, we can see that indeed large part of this weeds is now gone. I can toggle back the background map to see more clearly. There is still some room for improvement. Not all weeds are gone, so we can keep iterating like this, adding more examples, and at some point the tool will achieve good enough accuracy so that we are satisfied with the results. But for now, we'll move on to the next step. And to do that, we will choose which detection we want to move forward with. So I will choose the latest one with more accurate results and click proceed to analysis. And in the analysis step, we can slice and dice the data that we have generated previously in a number of different ways. For example, we can look at the diameter of the plants and see how it varies throughout the field. With the histogram tool, we can say that all the plants with diameter smaller than 9 centimeters should be colored in red, so we can see where all those plants are, and there are some interesting patterns revealing here. And all the plants with diameter above 9 centimeters are the big plants, so that's the majority of the field. But we can move the slider to the right and say that all the big plants are with the diameter over 12 centimeters. And then we can see that in this eastern part of the field, there are some bigger plants, and the rest of the field, there are smaller. We get this nice table here with a breakdown. So we can see that 40% of the field approximately is covered by plants with bigger diameter, while 60 is the smaller. We get this also in number of plants as well. But we can also look at other metrics. So apart from the diameter or area, which is another metric for the size, we also calculated the plant health using GLI and vari vegetation indices. So if we switch to GLI, the map will update shortly, and we can also use the thresholding tool to define what is healthy plant and what is unhealthy plant. So this can be also used to potentially reveal unhealthy areas of the field. And very important thing here to understand is that opposite to the vegetation index maps that are quite widely used in the industry, this data is based on individual plants' health. It does not include all this area in between the rows. So only the plant health of the individual plants that we have identified in the previous step is used for calculation. So this should give much more accurate metric. We are, of course, not limited to just 2 categories. We can add another category and define threshold for low, middle, and higher category here. And we can add as many categories as we want in this step. Another way of looking into this data is also to split the field into different zones and calculate different metrics. So using this zonal statistics tool here, I created this grid, which is 20 by 20 meters each cell. And for every cell in this grid, we've calculated a bunch of different metrics. One of them is the plant density. So we can see how the plant density varies throughout the field. So the red and orange squares here is where the plant density is lower, and the dark green squares is where it's higher. And with all that, The final step is to generate some reports and export the data. So to do that, we just head over to the Export tab. We have here the PDF report option that we can click, and here we can select which data layers we want to include in the report, and also the area that should be highlighted in the PDF. So let's select the orthomosaic layer and the plant counts layer, and zoom in a bit here and click Create PDF. And in a few seconds, the PDF will be generated. And here we get a page with the orthomosaic, just as a visual representation of what a specific part of the field look like here. And on the next step, we see the plant counts with the total number of plants, the average number of plants throughout the field. And on this page, we also see the breakdown by the plant health. So those three categories that we defined in the previous step. So this PDF can be just downloaded here and send over the email. Back to the Export tab, we can also download the zonal statistics output, so that grid with different metrics. And we can, of course, also download the plant counts as a shapefile or CSV file. So it can be used for further analysis in GIS software or some custom R scripts and so on if you're working with research. All right, that's it for now. I hope you enjoyed this walkthrough where we looked into the hardware on the Mavic 3M, how to plan the flight and collect the data with it, and then how to process it with Solvi and finally generate the plant counts. If you found this interesting and think it can be helpful in your work, make sure to head over to our website, solvi.ag, and sign up for a free trial and give it a try with your own data and see how that works. If you have any questions, drop the comment below or shoot us an email and we'll be happy to help. See you next time.